Hello everyone, welcome to another class. In today's class, we'll be dealing with the second part of refraction. See how far we go, and I believe that in this class we'll conclude everything about refraction. So please pay rapt attention and make sure that you're writing and paying attention to whatever we're doing right here. This is for the best, this is in order for you to have the best, and do great in your upcoming examinations. So I'll share my screen now and go straight into the platform where I explain this concept. Now, refraction part 2. I'm going to start by just quickly doing an overview of the definition of refraction, which has to do with, we say it is the change in the direction and speed of light rays when they pass through, or when they pass from one medium to another. And not just another of different density. So the two mediums are always of different what? Density. So we established that in our previous class. And then some things I want you to take note of is when light is refracted, the following things happen. Its direction of travel changes. Take note of that. Its velocity changes. Wavelength changes. So you can see a couple of things that change. But the frequency does not change. Frequency remains the same. So take note of this important concept. And I'm not going to waste any time. I'm going to move straight into the portion where I revise the formulas. And those formulas came up when we talked about the laws of refraction. Go and read the previous note and watch the previous video to make sure that, I believe the notes is sufficient for you, but to make sure that you have a recap of the law of refraction and the important formulas there. But let me just rehearse briefly. If I say light is moving from air to glass, this end that you see right here, let me put it in green for now. This end that you see in green is called the refractive index. So the refractive index is from air to glass. We give it in formula as sine of the angle of incidence, sine of angle of incidence in air over the sine of the angle of refraction over sine of angle of refraction in glass. You see that? So the concept is when you are moving from air to glass, you have sine I in air over sine R in glass. Straightforward. And this applies to when you are moving from whatever to whatever. So if I say perhaps I'm moving from glass to air now, it is still sine I in glass. So you see how it works over sine R in air. So that's how it works. So the one that is first here that appears on top, the one that is second here appears down. So that's how it's, even if you are moving from, let's say, water to glass, anything, water to glass is going to be sine I in water over sine R in glass. So that's how the principle works. So you get it. Another thing you must take note of, let me just break this into two, is that this movement from air to glass, now, if I was to express the formula in terms of speed, it will be the speed of light in glass over the speed of light in air. So it's reverse when you are talking about speed. Why do I say it's reverse? What is second here comes on top, and what is first here comes down. That's why I'm saying it's reverse. It's reversed when you compare it with the sign formula. So same thing applies to other things. When you're moving from water to glass, you get the refractive index by doing V of what? Glass speed over V of water. So where V is what? Speed of light in that medium. Speed of light in the medium. Speed of light in the medium, whether glass or water or air. Speed of light in the medium. So just keep this in mind because we need it later. And you know how we can relate formulas to each other such that, I mean, we can now say since we have A of n is equal to sine I in air over sine R in glass, and we know that it's also equal to V of glass over V of air. You understand? Sometimes you can use these two, you know, depending on what we are given. Sometimes you can use this, you understand? And sometimes you can use this and this together. You know how that works. So that's exactly what we're talking about. Take note of that. We are moving straight ahead. There's something called the principle of reversibility. That is when you are given the refractive index of one thing and you have to find the refractive index of another thing. It's so easy to do this, and that principle has to do with the fact that if you are given the refractive index of air to glass, you can easily find the refractive index of glass to air by reciprocal. So the idea is, if I have this and I find the reciprocal, I get this. And it applies across board. Let's say I'm giving water to glass now. I can get that from 1 over glass to water. So I don't need to waste time on this idea. This is the idea of reversibility. It's important, you know, as we go ahead in solving, you will see the usefulness later on when we are revising solving multiple questions. But just keep it in mind that if they give you, you know, refractive index of air to glass, we can easily get, you know, glass to air from there. So keep that in mind. Let's move forward. There is another concept I want to establish to you, the effect of total internal what? Reflection. So the effect of total internal reflection. Let me write that down. Effect of before I no, that's not what I'm going to. It's effect of refraction. Let me do refraction first. Effects of refraction. I'm going to talk about the applications of total internal reflection, but let me talk about the effects of refraction first. So refraction is responsible for bottom air, the bottom air, no, not bottom air, the bottom portion rather, the bottom portion of the river, of a clear river or a pond appears shallower than it really is. And this thing has to do with apparent real depth and apparent depth. Apparent depth is the way you see it, while the real depth is the actual depth. So if you see the water as shallow and you pull leg, you'll now discover, it's deep. Oh. So that's refraction. It's refraction that affects your eyes, that makes you see it as shallow. So refraction gives you the idea of apparent depth. So bottom portion of a clear river or pond appears shallower than it really is because of refraction. So that's you know, some applications of refraction or effects of refraction. A rod or spoon appears bent. Whatever you put inside glass cup, bent or broken, when you look at it from the outside portion of the glass cup, when viewed in a partially, when viewed a partial, when viewed in a case where, let me put it like this, sorry about that, when viewed in a case of partial immersion in water or any liquid. So keep that one in mind. It's refraction that causes it to appear bent from outside. So the third one is letters. Just give it straight up because we have quite much to cover. Letters in print, like these typed letters, seem to be narrow. Let's not just normal type letters. Just any, let's say you have even written something, or when you carry this thing, when you carry a glass and you use a glass to look at them, some particular glasses make them to appear narrow when a thick block, letters in print seem to be narrow when a thick block of glass is placed over them. So they are just saying, you know, written words or printed words appear bigger through, you know, a glass. So the effect of that is refraction that is responsible for that. So let's quickly dive into the next thing, and that is where we'll look at. I'm going to kind of have a reflection on what on some of the formula portion I talked about when I was talking about refraction in triangular prism. I drew a simple diagram then, but I want to draw a more comprehensive diagram now. Refraction in triangular prisms. If you open your note and you go back to that particular portion, that was the portion where you remember I wrote formulas like D equal to D1 plus D2, which is equal to I1 minus R1 plus I2 minus R2, where R1 plus R2 is equal to 60 degrees. And I said D is deviation. I want to explain that concept better now by drawing a triangular prism for you. Let me zoom in. Refraction triangular prism. I'll draw a triangular prism. And I mentioned before I wrote these formulas in the last guy, I said in a equilateral triangle, these formulas apply. So that means here is 60. Now let's explain the concept of refraction here. Can I even make this let me make this triangle bigger. So I want to explain the concept of refraction with this triangle, but I'm going to make it bigger. Is it not too big? I think it's too big. So keep in mind I'm trying to draw a equilateral. I can even draw something very perfect by just extending sharp, sharp, sharp. So let's say my incident light ray, this is it, it's coming from here. Do you see that? Now, your normal here, so this particular side, I'm going to use green to top that side. You see this side I'm talking about now? Yeah, this side. If I'm to look at my normal is the angle 90 to that side. And if I'm to draw it, it goes like this, something like this, angle 90 to that side. And that is the normal for the incident. This is the incident. Let me get my red pen again. This is the incident guy that is coming right now. And when he hits that place, we know that whatever angle the incident ray makes with the normal, that is the incident, that's the incident angle of incidence. Why? So keep that in mind. The idea here is that now, once you go through like that, the light does not keep going straight. This is where it's supposed to be going. If it was to be going straight, to keep going like this, right? No, let me check that very well. So if it were to be going the way it's going, to be going like this. Yeah. But then it bends. It bends. And let me show you how it bends. It bends The way we normally say it in physics is that the light in refraction, it bends towards the normal. You know, this is normal right now. We know that this is the normal. So we are not expecting that the light will bend, you know, away. Maybe to not bend like this, no. To bend towards the normal. So to bend downwards like this. Let me draw that as a sharp line. Or let me go again. So bent. So this direction is closer to the normal. So, but then since it bends, you see, this is the red line is showing you where it should have been going. But because of refraction, it bends. It bends in that black direction. Now, since it bends like that, we cannot say the angle of refraction is the angle that refracted ray. This is incident ray. This is the refracted ray now. We know that one. The angle that the refracted ray makes with the normal, this is normal. That's the angle of refraction. So I'm going to call this R1. I'm going to call this I1. Now take note of the fact that this red line here that is traveling is the normal, is the direction that we expected that, oh, this particular light will keep going. But because of refraction, it has bended. If you look at how much it has deviated now, you know, whenever you say deviation, you have a particular normal thing. Then we have an abnormal thing. Then the difference between the normal and abnormal is like error or deviation. So if you look at this particular line, let me be using green to point now. This particular line and the normal line. I mean, when I say normal line, I mean that the direction that we expect it to keep going if refraction did not occur. That red line. Look at the refracted ray line and the incident ray line. The angle between them is what we call angle of. It's not the angle of deviation now. We can say it is the first deviation because this thing has not yet come out. Okay. Let me first of all, let me tell you, I'm going to call it first deviation. So I'm going to label that angle. This is the angle here. I'm going to call it D1. You see why I'm calling it first deviation. Now, when the light has been refracted like that, it still has to come out. It still has to come out of the prism. And when it's coming out of the prism, let me again point out that in this portion here, there is also a normal. But when it's coming out like that, of the prism, it's going to bend. Going to bend upcoming, excuse me. It's going to bend downwards the more. Oh, let me try. I'm going to bend downwards. You see that? So let me explain now. Let me explain something. I'm coming. Let me see. To this normal now, to this particular normal, to this normal that we have here, this second normal, the refracted ray is serving as the incident ray now. You get the idea? It was a refracted ray before, but to this particular normal, it is not the incident ray. And so when we are talking about the angle between the incident ray and the normal, that will be this portion. And this portion now will be I2. While we are talking about now the movement of this refracted ray, if it were to be going straight, it's moving like this now, it would have been going like this. You understand? Now, if we compare that with the way it's bended, you know, the direction where it's bended towards, if we compare the deviation, we are talking about this particular angle. That's D2. That's why I said we have one deviation here, because this was where this one was traveling before. This one, this first case, that was where it was traveling before. Now, this is another case where the initial refracted ray was traveling like this. Then when it got outside, it bent again. So there's a deviation, that's D2. And then, since it was the refracted ray, but to this particular normal, this second case normal, this one here, it is not, it is a incident ray. So, and the angle between that incident and is the I2. So that's where all those concepts come from. Then another important thing is that if you look at it very well, the angle between the normal and the new refracted ray, because but this final refracted ray after coming out into air again, we call it emergent. You would have discovered that this one is called emergent. The final one that comes out is called emergent ray. Keep that in mind. So it's like the second refraction. You understand? After coming out, it's called emergent. The angle between the emergent now and the normal here, we can call that angle R2. R2. So that's it. Because that's how we work with the stuff. So angle between the stuff and the normal, the emergent and the normal is R2. Now, if I extend this emergent backwards, if I extend it backwards, there is an imaginary point where it will hit the red line. We now say the angle between the emergent and the incident. You see that the incident is the red line. That's the D. This is the D. And we are trying to make a point that D is equal to D1. That's what we wrote up there. D is equal to D1 plus D2. This will even relate to your math. Because you see this D2 that is here is vertically opposite to this portion. So it means this place is also what? D2. Are you seeing the idea? You get it? Yes. So it means that place is also D2. And if you now look at the rule of exterior angle, if you see this angle, let me use red on it now. This angle D that we are referring to here, this capital D, is an exterior angle that is always equal to the sum of two opposite interior. So, and if you look at the two opposite interior for this exterior angle D, the two opposite interior are D1 and D2. So D, that's where we got the formula of. And also another thing is that just by normal logic, in the entire motion, we had two deviations. From when we started the incident today, it bent once. It bent the first time. It gave us one deviation. That one that bended now serves as an incident ray again and bent the second time. So you should know that the total deviation will be the addition of the two sub-deviation, what I call sub-deviation, sectional deviation, the two half, I don't want to call it half, the two part deviations. You understand? So like deviation 1, deviation 2 will give you the total deviation. So please, I just use the prism now to explain this concept to you. So that's where the idea of D equal to D1 plus D2 came. Another thing is that you know that this D1, where we got the idea now that it's I1 minus R1 is very correct, because if you look at vertically opposite angles, we know that, look at it very well. Let me use black here now. This is where I am. I'm here, somewhere here. So I'm calling this angle, this I1 is supposed to be equal to this entire something, right? By vertically opposite angle. That is, we are saying I1 equal to what? D1 plus what? R1. Are you seeing that concept? Very straightforward. Very what? Straightforward something. Are you seeing it? That's how it works. So the idea here is now that I'm coming, hold on a bit. Okay. Yes, okay. So the same idea applies when you say, okay, Yeah. Yeah, so sorry, I got distracted for a bit. I1, yeah, see it here, vertically opposite to this. So we have D1 plus R1. That's clear by vertically opposite. So we can easily say what? D1 is now what? D1 will be what? I1 minus what? R1. That's very clear. So the same principle applies for I2. If you look at I2, right here, incident ray making its angle with the normal, this and this. There's a way to prove that D2 and R2 rather, D2 and R2. You see, this is cool. Okay, let me do it this way. There was something I wrote wrongly here. Coming. This I2 that you see here, let me clean it. The I2 in this case is not down here. It is rather up here. It is the angle. See it. This is the incident. This is the incident. You see, this one is the new incident. I'm just pointing at that line. You understand? I'm using that idea to point at the line. Let me remove that stuff now. So that line is coming back and it meets the normal. See the normal right here. So just look at where they meet. See the incident. The full incident angle here is here. This is it. So this is I2. So if you look at the lower part, that is also supposed to be vertically opposite to this entire thing. Let me use right there. This entire part. Vertically opposite to this part. I2. You see that idea? So, and that entire part that you're looking at is divided into R2, that's this part, and D2, this part. So that's where the idea comes in. I2 equal to what? D2 plus R2. And the same thing applies to say D2 will now be what? I2 minus R2. So I'm just trying to validate these formulas that I wrote for you before. That's how we got them. So, but mind you, most of the time in physics, know your formula and you are good to go. But this is the physics. This is it. So we are using, this is how we use mass in physics. Vertically opposite, no discussion, no exterior angle equal to sum of two opposites, all those kind of things. So it mass helps you to be able to explain physics very well. So that's how we establish most of this formula that you see right here. And there's a way to prove. And there's in some of the formulas which I will rewrite again. There's an A that kept appearing. That's like the the angle at the top, the angle right here. That's in an equilateral triangle. A is what? 60 degrees. That's the angle at the top right here. So and that A now, we said your R1 and your R2 are equal to 60 degrees too. We can prove that. If you look at R1 is somewhere here. Just this portion. Just this portion here. R1 and your R2, just this portion. If you look at that, there's a way for us to show that those two. But just keep it in mind that your R1 and your R2, they will always add up to your A. So I don't want to bother you with showing that now because that's not a possible exam question. It's just more like proving the physics. I don't want to bother you with all this. But just know that in mind that your R1 and your R2 will yield your A. And you have seen where A normally lie. So that's just to confirm those formulas. So we'll use those formulas going forward. I know this is something for you to, if you follow why I'm teaching now, you will see the idea that we're using most of the time is vertically opposite angle and all of those stuff. Let me redraw the diagram in a clean fashion now again before we move forward. And I will rewrite some of the formulas I wrote before that had to do with A. But those formulas, we are not proving them for now. We are basically knowing them. We have just proven the part that has to do with D and R1 and all of that. So this is it. Let's say this is the first incident angle. This is the normal. So that is I1. You know that this one is supposed to keep going like this, but it bent. And since it bent, the deviation from the normal, the first one is D1, and the angle that the bent one makes with the normal is R1. But this one that has bent now is now incident to a new normal, and the angle between it and that normal is I2. And this produces another bending again of what we call, this is the incident ray, this one right here. I started it. This one right here is refracted ray, and the guy produced finally is emergent. So since this guy was going like this before and now bent again, this is a D2 now. And then the angle between the normal and the new bend is R2. That's just what I explained. And here we say that I1 equal to R1 plus D1, which is just based on vertically opposite. We say I2 equal to R2 plus D2, which is based on vertically opposite. Very straightforward something. So we now said even if we draw this emergent ray backwards, like here, draw it here, and it meets the first guy, like this initial incident guy, this first guy, the angle they make between each other is capital D. And just by using triangle rule, because this side here is also equal to this internal side, D2. So, and D will now be equal to D1 plus D2, just based on the rule of exterior angle equal to sum of two opposite interior angle. So that's just what I explained just now. We have to move forward. I have to explain that so that you see the idea of refraction. Let me write some of the formulas that I wrote before. And I call this place A, which is 60 for equilateral triangle. Then I wrote some formulas before which are important. A plus minimum deviation. And here we said minimum deviation is 2I minus 2R. We said A is 2R. Don't worry, we would establish some of these things when we start solving questions with this. We established that N equal to sine I over sine R. And it's also equal to sine 1 over 2 into A plus minimum deviation over sine A over 2. So we've established these things. Keep this formula in your reservoir. Don't play with them. Read them. When we start solving, you will now see that they are instrumental, they're important. Another important formula that will be useful when we are solving is also from Snell's law. And commonly, when you see us using glass, water, air, yeah, a common way to write it generally is to just write it as N1 sine theta 1 equal to N2 sine theta 2. Because the meaning of this is just like writing sine theta 1 over sine theta 2 equal to N2 over N1. So this is another way of stating Snell's law. So in Snell's law, where we just stated, so refractive index, the ratio of the refractive index, this is another way of stating Snell's law. So this is it. Keep this one in mind. Let me write it down here. So it's an important formula too. N1 over N2 equal to sine theta 2 over sine theta 1. There's a switch. Or if you say, that's what I wrote here, see it. N2 over N1. Then you have sine theta 1 over sine theta 2. So both sides, there's a switch. Do you know what meaning of switch? Like this place is not something that is not N2 over N1 equal to sine theta 2 over, it's not like that. Are you seeing what I mean by switch? It has to be up, will now be what? 1, and here will now be 2, because this one is 2, 1, 1, 2. That's how it works. Don't go and make mistake of 1, 2, 1, 2 or 2, 1, 2, 1. So the rule is that no matter how you write it, make sure that you are writing switched. You are writing it switched. You'll see the importance of this formula later on. So switching it, you have N2 over N1 equal to sine theta 1 over sine theta 2, or N1 over N2 equal to what? Sine theta 2 over sine theta 1. Take note of that. So yeah, please. So moving forward in class, I will now go straight into the applications of total internal reflection. Catch a breath. And let's talk about the applications of total internal reflection. Catch a breath for like 1 or 2 minutes. Let me establish this concept to you. Applications of total internal reflection. Catch a breath, catch a breath. We just talk about some theoretical stuff now, which you have to take note of before we move forward. Yeah, so first thing, all right, is optical fibers. Total internal reflection are used in optical fibers. So, and this is, okay. Let me write it like this. The concept total internal reflection is used in optical fibers. And what are optical fibers? Optical fibers are thin, T-I-T-H-I-N, thin glass thread of high refractive index. For transmitting electromagnetic waves. So just let's leave it at that. Next one is submarine periscope. Total internal reflection is utilized in submarine periscope. Where mirrors in a simple periscope are replaced by right-angled isosceles prism. To prevent occurrence of multiple images. So number 3, the appearance of shiny object as an application of, e.g. diamond. When those things shine like that, it's an application of total internal reflection. Total internal reflection applies for the rainbow. Number 5, it applies in binoculars or short telescope. Number 6, it applies in bicycle reflectors. When we say it applies, like applications or uses or importance, so anyway they ask it, these are the uses of, or these are where you see, total internal reflection exhibited in daily life. Fish fields too. Fish field of view underwater. Excuse me. Fish field of view underwater. Let's see. I'll quickly talk about what a mirage is. That's a separate subtopic. It is the optical illusion of a reflecting pool of water on road surfaces. Keep that in mind. It's associated with hot desert. It is associated. It is associated with hot desert or hot road ways when you are at a distance. You see something when you are traveling and you see something like water, and you say, water is in front. And when you get closer, the water disappears. That's a mirage. It's because of the heat and and you see it, optical illusion, reflecting pool of water on road surfaces. It's an illusion, it's not real. So it's because of the weather at a distance, when you're at a distance. So it can be explained by refraction and total internal reflection. But it is more of refraction. So that's a good point to make before we go into the next thing. And the next thing we're looking at is refraction in lenses. So the working principle of mirrors is reflection. The working principle of lenses is refraction. So let me establish that. Refraction in lenses. The idea here is I'm going to establish what a convex lens is, types of lenses. Number one, I'm going to call it a convex or converging. In this case now, I've established, I sounded something to you during mirror that they are not the same. In the case of convex mirror, it is a diverging mirror. But convex lens, it is a what? Converging lens. So please give me a minute. I have to just pick a call for a bit. Excuse me. What's up? What's up? No. I'm not at home. I'm even in a class right now. So please, I'll have to call the call. I'm very sorry. I'm in a class right now. So thank you for permitting me to quickly shut that off. Convex. See, the point I'm making here is please don't be reckless and say, oh, converging mirror is also, converging. Convex mirror is also converging mirror. No, I established to you that in the naming of mirrors, convex mirror is also a diverging mirror, and that concave mirror is a what? Converging mirror. But yeah, now lenses, and I studied that is a different thing for lenses. Convex lens is converging what? Lens. Converging, convex lens, or converging lens. Just read. The whole idea of painting this to you is that don't make the mistake because you have read and you overread. And you already know that your teacher made noise that it is different. So, and then for the concave, it is also called diverging lens. Keep that in mind. Let me quickly define them. Converging lens. Based on what we know about converging and diverging, let's say, okay, the first one, convex or converging lenses. That is these are lenses. These are lenses which bring light rays together at a focus. So you see the point. Let me draw it for you, the way convex lenses work. When you bring together, that means you are converging. You are bringing things together. Let me redraw this my diagram. I need a curve. And a curve. Thank you. So now, if light rays are coming from here, and let's call this one the principal axis at the center. This one coming from here. So everything is coming from here. And the idea is that they bend. As they enter this thing, they bend, but their bending is such that, why is this guy bending like this? Okay. They bend, but their bending is such that they are bending. They are all bending to meet at one point the focus. Do you see the idea? This is this is the diagram of convex lens. So converging, when they come together to meet, it brings light rays together, the focus. Why the opposite one is concave or diverging lenses or lens. Let me just call it lens now. So these lenses spread out, You know, when you diverge, you spread. You spread light rays, or the way we normally use it as we are defining, before. We say these lenses appear to spread light rays from a focus. I'm going to draw a sample of a concave lens for you. So let's say light rays are coming like this, coming like this, coming like this, coming like this. Now, the idea is when they meet this mirror, they go up like this, they go up like this, they go up like this, they spread like that. Oh, what did that one do? They go like this. So if you trace, you see the idea of all these ones is that if you trace all the parts from the other end, all of them appear to be spreading out from a focus. So these are lenses that appear to spread light rays from a focus. If you call this a focus, where all of them link back to. They are spreading out, but if you trace them backwards, you see the idea? They seem to be what? Spreading from a focus. So let me add here that for convex lenses, they are normally thick at the center. Obviously, you can see that from the diagram. They're thicker at the center. By this one, they are thinner. They are concave lenses are thinner at the center. Keep those points in mind. Yeah, keep them in mind. Also note that the idea of the definition of terms like pole, focus, center of curvature, they are similar to, just go back to the one that you read about mirror, and I've just changed the mirror words to lens as similar definitions to the ones for mirror. So we don't need to repeat that. Go and reread that and change those words too. So if they ask you about lenses, in those cases, you say, okay, what is focus of a lens? Just say, okay, just change the mirror words there to lens then. So to that of mirror. So those are definition of concepts. So they apply across board. So the idea we are going to straight up is catch a breath for a bit. I want to make sure that I'm not missing anything I have to tell you. Okay, let me say notes before I go into images formed. For convex lens, they form now. We know that convex lens is the one that is also called converging lens, and concave mirror is the one called converging mirror. Now we notice that when concave mirror was forming its image, whenever it forms its image on the same side, we say that image is real. So for concave mirror, same side image, but we want to establish now that whenever we talk about lenses, it is the opposite side image that is considered as real. That's a special point. Keep that in mind. Just keep that point in mind. When we're talking about concave mirror and we're trying to form their images, when images were formed on the same side as the object, those images were considered as real. But now when I want to now discuss the formation of the images of a convex lens. But I want to tell you beforehand now that when it is formed on the other side, the opposite side, that is when it's a real image. So just keep that concept in mind. Now let's quickly now go into subheading. Images formed by convex lens. This particular section, I'll be trying to draw and explain. So keep all of those things in mind. Images formed by convex lens. I'm going to start with the case of, excuse me, object at infinity. And I will draw before I now write the features. Object at infinity, this is what it looks like. I have my convex lens. I have my rays. Let me first of all have my principal axis. Come in. Principal axis first. I know normally I have my focus, then I have my 2F, And then I normally identify that whenever my object is somewhere beyond my 2f, that's when it's at infinity. So it is bringing rays towards my convex lens, and then it's bringing the rays towards it. And then my convex lens, of course, focuses this thing and brings it to a point that brings it to the focus on the other side. So this is how the object at infinity is how it works to produce the image at focus. So you see the image at focus, and the features of those image, I can say the image is, see the point of the image, it is real. One of the reasons why it's real is, like we said, for convex lenses, once you form it on the opposite side, it is real. B, it is inverted. So if the object was like this, let me draw it like this. If the object was like this, then the image is definitely facing somewhere down. Let me not put it up. Yeah, let me put it down. Image is somewhere. Yeah. So it's inverted. Call it inverted, and then it is formed at focus. So that's the basic point. We'll not waste time here. It's formed at the focus. It is inverted, and it is real. Another thing is, I don't need to draw anything on this side. I mean, let me just take this red guy off. Yeah, delete it. I don't need to draw anything. So just put your focus there. So take note of that. Also, you might want to go to the case of the concave mirror and check when we put something at infinity, the object at infinity, you don't need to draw anything for the image. So if I drew an image there, just go and remove it and leave it this way. So the features remain real, inverted. You don't need to see it. Just know that it's inverted, and then it is formed as focus. Let's move forward. 2, when we have the object where we call beyond 2f. So if I have it beyond 2f, what I mean by that is this is my lens. I have my principal axis. F is normally here. 2f is normally here. Beyond 2f, yeah, it shows somewhere here. If I say this is my object now, then I send the upper ray here, upper light ray here, and that one bends down all the way. As it's bending, it goes through the focus here. And then I send a diagonal one that goes through. That goes through. This is how this one forms. Oh my God. Send the diagonal one that goes through the. Okay. I think where I made a mistake is okay. I'm coming. Is my focus is not. It's not kind of the same with. So I want a distance. Focus here. Focus here. I want the same distance, something like that. So if this one passes through the focus, good distance. Okay. Then here, this one goes to the center. Getting my drawing one. Okay. And yeah, they meet like that. Okay. So that's how we do it. This one goes through here, goes through here. And then this one comes down like that. This one goes through here. And then they meet here. Then we know that 2F is somewhere here. So the image will be formed here. So the idea is, if everything is drawn right, these two things, this one is bigger. It's definitely going to be bigger than this guy. So you have something like this before, and then now you have something a little bit smaller. So the idea is, the image is, number one, is between F and 2F, as you can see. All right, and 2F and 2F, as you can see it. See this area. The image is between what? F and 2F. Then the image, we see that it's inverted. And we see that it's diminished. That is of lower size. It's diminished. Smaller size. So just take note of those important things. Don't need to stress. Let's go to the next one, straight up. And that's the case where we have the object at 2F. So this case we just did was beyond 2F. New case is object at 2F. So let me drop convex lens again. Oh. Yeah. So this is F, and this is 2F. I have my object at 2F, and then I run the same analysis. I do this to here, and then it bends down, passes through a new focus, and goes up here, goes, and here I have 2F, up, have 2F, keeps going, okay, keeps going. So the other analysis is run through the center. Oh my God, that's bad. Going. Let's do it again. However, I want to run it. I must run it through the center of that place. And it must, all things being equal, if this is done rightly, let me just draw it. Well, oh my God, sorry. Okay. So sorry. I think I stopped sharing my screen for a bit. So let me reshare. Yeah, so this was where we were. And I said, if all things being equal, I draw this to pass through the center properly. Brilliant. Oh, I could have made that line strong. I mean, pass through the center properly. Let me do it again. One last try. Forgive me for this, but exactly. So all things being equal, if it passes through the center properly, it's supposed to be formed at 2F, and then it's going to be the same size as the object. So the idea is, when the object is at 2F, the image is formed at 2F as well, and it's same size. Same size. Now, there was something I did not note here. Since the image is formed on this other side, as you can see, it is real. So opposite side, we know that that's a real image. I think I noted that here. Yes. So also the same thing applicable here is formed on opposite side. We've established that. We discussed that before now. It is a real image as well. So real image formed at 2F, same size. So the fourth concept now is when we now have the object between 2F and F. Object between F and 2F. And the concept of that is you have your principal as this running through. Let me make it straight up. Let me run it through here. Oh my God, why is it bending? Okay, that you can manage that. So this is F. Let's say this is 2F, and we have the object between F and 2F. Let's see where the image will be formed. It runs through here and bends, passes through the focus down. This is focus here, and this is let me keep extending this guy. This is 2F. Yeah, let me extend this line. So this is 2F. Now the other one is to run through this place, the center. So it forms something here. So did I note that this one is also inverted? Yeah, it's inverted because you see it. This is the same size, but it's what? Inverted. So this one is facing up, this one is facing, this one is inverted. So let's not forget to note that. So for this one, the image is number one, from what we can see, the image is bigger. Yeah, if I drew it very, very well, perfectly, let me extend this, and this. The image is actually bigger. So let me see if I can redraw it more perfectly. Because right now it looks as if the image is same size, but let me draw it, but let me try to draw it perfectly. I mean, maybe that. Yeah. Hold on, just hold on. Get the idea I'm trying to push out. This one is inverted. So let me try to redraw. Let me pick this guy out. No. I just want to pick this line. Oh, okay. I'm gonna clean the line. So I'm gonna run it. I'm gonna run this guy. F to F. Line keeps going. I'm gonna run this guy through F. I think what I even have to do is to trace it well from here first. Okay, so this is the object. Trace it up. Then I trace it to here. Okay, run it through F. And then run it from the top to the center, down. Exactly. That's why I say if I drew it properly, I discover that see how big it is. So in this case, the image is, enlarged, bigger size. It is formed beyond, you see that it's beyond 12. Beyond 12. It is inverted and it is real. It is the form of opposite side. It is real. It. So this is like the object, and this is like the image. See that comparison? So please, let's go straight to the next one. No wasting of time. And in this case, we're talking about when it is now at infinity. When the object, no, sorry, the last one we talked about, no, was between f and 2f. Okay, between f and 2f was what we just talked about. Let's talk about when it is at f now. At f. Object at f. Sorry. Object at f. So for object at f, of f, 2f. So if I put the object at f right now, and I run my normal analysis, run this guy, through f here, to f here, and I run the other one. No, run it through the center. I discovered that they never meet. If I'm to draw it very well, perfectly, right now the thing is not cooperating with me. I intend to, yeah. So if I draw it perfectly, discover that these guys, they keep going their separate ways, they never meet. So our image is formed at infinity. So image, when you place the object at f, your image for a convex lens, image is at infinity. So at f, you have your image at infinity. Let me see if I can get out some other features for you. If you place it at f, so it's just keep that's, let's just see it as the only feature. So image is what? At infinity. Just keep that. Since you can see it, the image is at infinity. Let's go to the next one. 6. The sixth concept is when you now move it between f and p, that is between f and the mirror itself. Catch a breath, catch a breath. Let me draw that. Object between f and mirror. Let's put it f and lens, not mirror. This is not, we are talking about lenses. F and pole. And you see that even though I've not been labeling it all this while, this center here is the pole, like, and that's how it does too in the mirror. You understand? So pole, so you can label it in the others. So but the idea is now, this is where we are, where the object now is between stuff f to f, f to f. The object is between, this is where your object is now. Object is somewhere here, and this is between f and what? Pole. This is between f and pole. So if I have my object, then I'm going to run the normal something. It bends to the focus. Yeah. And then the other one bends to the center. So, and to trace them, sorry, I don't know what I pressed again. I just hope that you can hear me during this period. I hope that you can hear me. Let me share my screen again. I hope I can stop pressing whatever I pressed. So, let me see if I can redraw, because I think I'm missing something. So if I bend this guy really well, like this, then if I move this one like this, yeah. If I trace them backwards, these things, they are tracing. meet somewhere, and that's the meet coming. The tracing right now is kind of let me try to do this again, because I mean must be able to trace it such that they meet somewhere around there. So yeah, so let's go with so tracing. So anyways, yeah, so if I trace this one, we meet somewhere here. So the idea is the image is, first thing I notice, I would say virtual, because this are around, it's not formed on the opposite side, which is normally this area. This is normally, let me draw this thing. This is normally this area. It's not formed on those sides. It's formed behind. It's formed this at this side. That's the virtual image. It is not inverted. You see it. The image. This is the image bigger. This is the. It is not inverted. They are pointing up, both of them. It is erect. Another thing we notice is that it is enlarged. The image is enlarged, bigger size. And then what else? It is formed beyond 12. It's formed beyond 12. So just keep all of these concepts in mind, because we have established the images formed by convex mirror right now. I will just talk about the image formed, just the way there was also just one concept for the image formed by that was convex mirror. Now there is only one concept for image formed by concave lens. And that concept is that all their images are, they are all, we just talked about convex lens. Now we're talking about concave lenses. They are all their images here now are all, listen attentively. Let me pull that up for you. They are all virtual, erect, and diminished. So just like the convex mirror, concave lens, convex mirror, two of them are diverging. Concave, this is like concave or diverging lens, and that's convex or diverging mirror. So you get the idea. Like anyone in both cases that is both converging, it will have the same characteristics. And you know that in mirror, the one that is converging is concave. So it will have the same characteristics as a convex lens, because convex lens is converging. That's it. That's a big idea. Then in mirror also, convex mirror is the one that is diverging. Why? In lenses, it is concave that is diverging lens. So two of them will now have the same. So that's why both images formed by them are virtual, erect, and diminished. And you remember during mirror, we raised up the point of VET. So a good point to remember. And the images here are always formed between the principal focus and the lens. So keep that in mind. We've made that point, and then we'll just make some simple statements, just before we call it a day in this class, just to remind you of what a simple microscope is all about. Simple microscope is formed when a convex lens gives an enlarged upright virtual image placed inside the principal focus. So just take note of that. I've talked about the microscope before, yes, and that is very similar to what I said before, but you can just add this one to it. It's a simple microscope. I've talked about it before. So we know that it is used for reading and studying biological specimens. Take note of that. That's a good point. So there's having spoken about that now, I will talk about just another salient point, another important point, and then we'll call it a day for today's class. Lenses, let me say spherical aberration. Last thing I'll talk about today. So the inability, this is the inability of a lens to refract wide beam or rays that are far from the principal axis. Inability to refract them through a common focus. But through a nearer point than the focus. So it's just like you are trying to change the focus from where it ought to be to a nearer point. So it is when a lens, spherical aberration is the inability of a lens to refract wide beam through a common focus, but through a nearer point than the focus. So it's more like saying you are refracting light through a nearer point than the common focus. You refract them at a point before. So let me say, for instance, if I have a lens, so I'm painting the picture of what is being said here now, and light is coming, and I'm refracting them, and I'm supposed to refract them here now, the common focus, and I end up changing it and refracting all of them to a point before. This point is nearer. So this is suppose the normal focus. This is the actual focus, but this is the nearer point. So if you make the focus, if you make them to focus early before the actual focus, that's a concept of spherical aberration. So it can be minimized by allowing light to pass through the center of the lens only. Take note of that. So having done this now, call it a day in today's class, and I will see you in our following class. So we have concluded on refraction. We'll now, whenever we meet on this topic again, we'll solve questions actively, preparing for exam, like revision stuff. So let's go. I'll see you in the next class. Please keep reading, keep being serious. It's important for your success in exam and, fundamentally for your success in life. I'll see you.